Good morning, one and all. Welcome to the FDP, which is a 5-day FDP on recent trends of EV technology. I am Usharani, Assistant Professor, AAA Department. So we conduct this FDP from NSRIT, which is an autonomous college, NSRIT, Nadinpalli Satyanarayan Raju Institute of Technology. So we are autonomous since 2020. So formally, our college was named as WITS, which was established in 2008. And NSRIT, the location wise, we are located in Visakhapatnam, Suntiam, on the Pendurti and Anandapuram highway. And we have been autonomy since 2020, and we have been accredited with NAC A+ grade, and also we have NBA accreditation for CSE department. And also we have branches, 7 branches in our department, which are CSE main branch, CSE AIML, CSE data sciences, and we have ECE triple mechanical civil. And also we have MTech in 2 departments, which is triple and mechanical. And also we have a MBA graduation program in SRIT. So I would like to introduce our HOD sir, Dr. RSR Krishnam Naidu sir. So, Krishnam Naidu, sir.
Hello, ma'am. Thank you. Thank you very much.
The session is over to you, sir.
Yeah. Thank you.
Yes, sir.
Thank you, Usha, ma'am. Ladies and gentlemen, a very good morning. Myself, Dr. Krishnam Naidu, Head of the Electrical Department. Once again, a very good morning to one and all, and welcome to the 5-day faculty development program on recent trends in electric vehicle technology. It is my pleasure to introduce our esteemed guest for today, Dr. Gururaj MV from the renowned Indian Institute of Technology, IIT Kanpur. And today, we are honored to have Dr. Gururaj as our guest speaker. He will be sharing his valuable insights on the topic of recent trends in the electrical vehicle technology. And Dr. Gururaj's profound expertise and expensive experience will undoubtedly inspire all the participants and ignite their curiosity in exploring the vast potential of electric vehicle technology. I encourage each and every one of you to actively engage in the session. Seize the opportunity to interact with Dr. Gururaj sir and gain valuable insights that can shape the future of electric vehicle research and development. Without further delay, I extend a warm welcome to Dr. Gururaj sir. Thank you for accepting our invitation and grace us with your presence today. We eagerly anticipate an enlightening session with you, sir. Please join. I request all the participants to please join me in giving a virtual round of applause to welcome Dr. Gururaj sir for Faculty Development Program. Thank you, sir. I request Dr. Amaleswari ma'am to speak out the one-page profile of Dr. Gururaj sir and his contributions to know more about Dr. Gururaj sir, and then we can start the first day FDP successfully. Thank you, ma'am.
Good morning, one and all. Dr. Gururaj MV received BTech degree from Visvesvaraya Technology University, Belgaum in the year 2009, MTech from NITK Surathkal in the year 2015, and PhD degree from IIT Roorkee in the year 2020. Now, sir is faculty in Department of Electrical Engineering, IIT Kanpur. He has industrial experience in Ozone Group and Philips India Limited. His work is published in various international journals and conferences, including a patent. And he received Best Paper Award in IEEE IAS sponsored conference in 2021. And also POSOCO Power System Award, PPSA, in the year 2021. And AWSER Best Science Story Award under postdoctoral category in the year 2021. And his research include renewable penetration challenges to the microgrid, machine learning applications to power systems, power converters for EV and its interfacing challenges, power electronic applications to power systems, microgrid control. Currently, he is guiding 5 MTech students and 4 PhDs, and he delivered research talks in electric vehicles at various IITs. He is co-PI for a US-India collaborative for a smart distribution system with storage, and he is PI for 2 projects, and they are having a funding of, one is having funding of 25 lakhs from IIT Kanpur. So when we see Sir webpage first profile, we can see his dedication and hard work to achieve any goal. So with those words, we'll get motivated, sir. And I request you to go ahead with the session, sir. We welcome you, sir, on behalf of all of us of this FDP, sir. Thank you, sir.
Thank you, Dr. Ramaleshwari and Dr. Krishnam Naidu, sir. I mean, am I audible on the first go?
Yes, sir, audible, sir.
So thank
Yes,
you so
sir,
much.
audible.
Yeah. Thank you very much, for giving me an opportunity to be the part of a very important FDP, which is recent trends on electric vehicle technology. It's a very trendy topic, and I really thank you for considering me as a part of this FDP. Now, without further delay, I would like to start discussing. Just a minute. Right. I hope my screen is visible to all of you, right?
Yes,
Is
sir,
my screen
visible, sir. Visible, sir.
Good. So the topic that I have chosen for discussing today with all of you is power converters for EV and its interfacing challenges. So let's start. So these are the contents for today's discussion. First of all, I'd like to discuss about motivation towards electric vehicle, benefits of electric vehicle, having electric vehicles in the system, types of electric vehicles in Indian context, where we stand today, what are the challenges as a country that we foresee to have large-scale electric vehicle penetration into the system, and what are the typical infrastructure, charging infrastructure that EV consists of, charging standards, and then we'll discuss about power electronics converters, impact of EV on the power system, other power quality issues as observed, and varieties of real-time simulation tools that I would like to run through, so that you'll get an idea, like whatever energy management schemes or charging algorithms that we develop that need to be validated in real-time simulation tools before we think of implementing in a field level demonstration. So I'll just give you an overview about the various real-time simulation tools that we generally use, and some typical case studies, some research works that we have carried out with our students at IIT Kanpur regarding the electric vehicles. So with this, I would like to begin the first content of today's discussion. It's about motivation towards electric vehicle. The key motivation, as you are all very familiar about, is enormous emission of carbon dioxide, carbon monoxide, and all these toxic gases into the environment. Right? Nobody wants to inhale carbon dioxide, carbon monoxide. The body is designed to inhale oxygen. But unfortunately, we are in a world where we have to pay a very high price to have a pure air. So it's our own mistake that we bent towards a lot of fossil fuels, and now we are paying the price. Nevertheless, the whole world is looking forward to undo the mistake that we have done by switching over to renewable energy technology at the grid level. When we think about electrical energy conversion, simultaneously the whole world is looking forward for replacing fossil fuel based conventional IC engines with the electric vehicles driven by the batteries. So this is the key driving factor that I can see that why the whole world is looking forward for electric vehicle. You can see here a head-to-head comparison has been given between electric vehicle and a gasoline-based vehicle. So there is no tailpipe emission, whereas there is a greenhouse gas emission or pollution can be seen in gasoline-based IC engines. Utility company, it depends upon the utility company because we require electricity as a key input for our vehicles. It depends upon oil-based companies. 100 plus is the mileage range in the electric vehicle and 300 plus is the mileage range in gasoline. That we need to work it out. And there is one critical aspect of electric vehicle is the charging time is quite high as compared to the gasoline based vehicles. But there's so much of research being carried out, where the charging time is going to reasonably decrease with ultra fast charging stations in place. And the batteries technology is also evolving very quickly such that batteries can able to quickly cater to the need of 10C charging, 5C charging, and all these things. So the benefits of electric vehicles: lower running cost, right? Though the manufacturing cost and initial cost for EV purchase could be high, but running cost would be less. The petrol price, the diesel price is so rocket high compared to that EV per unit charge. That too, if you have a charging station based on solar panels, so it's almost negligible, I would say. So, and low maintenance cost as well. Zero tailpipe emission, tax and financial benefits are anyway there. Petrol and diesel use is destroying our planet, which is a main motivation factor, as I already told. And EV are easy to drive and less noisy. Convenience of charging at home and no noise pollution as well. So need for EV. So there was a Paris Agreement in 2015 where most of the countries, 196 countries have participated, and they've pledged to reduce the carbon footprint by 2 degrees Celsius. So that is the reason why the world is looking forward for EV. So helps to reduce overall carbon footprint, dependency on fossil fuels would decline. And the peak loading of the grid can be reduced. Not only the reduction in carbon emission, having EV in place, you can decide when to charge and when to discharge. So then it's a mobile storage unit that is moving around a different part of the distribution system, and you can call a specific or a set of electric vehicles at a specific node to discharge at a given point of time. If there is a peak and if there is a voltage drop, then the electric vehicles can be pulled and they can be utilized to maintain the flat load profile. And the ancillary services can be rendered, like, if somebody is interested for power quality aspects, improvement in power quality aspects like reduction in total harmonic distortion or rendering some reactive power support to the system. So having battery and the associated converters, one can carry out this exercise as well. So, and not only that, revenue for the prosumers. If somebody is interested to participate in demand response program while having electric vehicle in place, so he can utilize this electric vehicle to earn some money as well. And not only this, there is another important aspect of interest from power system engineers is the resiliency thing. I'll discuss about a case study that we have done here towards the end of my presentation, where resiliency improvement is a very important aspect, and that can be achieved by using electric vehicles. So types of electric vehicles: hybrid electric vehicle, where a small electric motor and battery supplement is placed. The IC engine is used and there is no electric charging here. So battery is placed, but the fuel input is conventional fossil fuels. And there is plug-in hybrid electric vehicle. It's dual fuel and dual traction. That means there is a battery units that are connected, and you can plug into a charging station and you can run the vehicle, or you can have fuel input as well. It's like multi-input, multi-dimensional vehicle. And a battery electric vehicle, this solely works with battery, and there is no scope for fueling the vehicle with the conventional petrol or diesel engine based fuels. So, and there is a fuel cell based electric vehicles where fuel cell is used as a main ingredient or main driving force for the electric vehicle. So EV in the Indian context, by 2040, the goal of this country is to reach to a point where we can see maximum EV penetration as close as possible to 100%. What is really hindrance for achieving this? So I have listed out some of points here. One is lack of EV charging points or stations. Wherever we go, only we see gasoline based charging, gasoline based petrol pumps or diesel and petrol based petrol pumps are there, but hardly we can see any EV charging stations or points. So this is, you need to enhance the infrastructure. High battery cost, because 40% of the overall electric vehicle cost is due to battery alone. So unless we bring in with the specific technology which can meet out the requirement of the battery need within an electric vehicle, say you need to have high power density, fast charging capability and all these things, along with lower cost, then EV would become more attractive. And that is not yet been achieved as of now. And high charging time, that is the another reason. We need to develop good converters capable of delivering the charge requirement of the battery as quickly as possible. And the typical users concern over long range of travel, regulatory concerns as well. So EV in the Indian context, nevertheless, you can see since 2020 May, there is a sudden shoot up in the purchase of electric vehicle across the country. So if you see the overall EV market in India, nearly 22 cars per 1,000 people. That means two-wheeler ownership is among the highest in the world. So two-wheelers account for the largest share of this market of up to 62%. So the penetration of electric two-wheelers is projected to reach up to 15% by 2025 from 1% currently. So there's a lot of scope being seen. In Bangalore, I have taken some facts that you can see by 2030 the projection is 30% in two-wheeler purchase, and three-wheeler it's about 70% as compared to the present 40% or 10% when we speak about two-wheeler. So this is the figures which indicates that there will be significant purchase of EV that can be seen in future. A typical EV charging infrastructure looks like this. So you can see here there are 5 important aspects. Socket outlet. This is a port of the charging station which supplies charging power to the vehicle. And plug, you can see here, this is a plug which is connected to a charging station, which will help to connect the cable from between the car and as well as this charging point, the charging panel, and the cable which the connector which connects the EV charger to the vehicle, and connector, the other end of a cable which interfaces the EV, and vehicle inlet, the port on the EV which receives the charging power. So EV charging level standards, there are 3 charging level types, level 1, 2, 3. Voltage level will be around 120 volt, 240 volt and 480 volt accordingly. And the voltage level is exactly suiting the requirement of the vehicle. So less than 1.8 kilowatt is your two-wheeler or a small three-wheeler. 19.2 kilowatt is a bigger vehicle compared to this, and 50 kilowatt to 150 kilowatt could be a large vehicle like electric vehicle, bus or truck or something like this. So there's different charging standards. Combines charging system, CCS, what we call it as. It's a very renowned standard, open international standard. This is a standard for charging electric vehicles. Combo 1 and Combo 2 connectors are used to provide up to 350 kilowatt. The CCS allows AC charging using type 1 and type 2 connectors. And this charging infrastructure encompasses charging couplers, communication, charging station, EV, and various functions for the charging process such as load balancing and charge authorization. So here I've given you a picture of how a typical charging port looks like. There are 5 important components present. One is PE, what we call it as protective earthing. It's an earthing point which is given in a green color, which will help to protect from any leakage. Hence, the human being or personal engaged would get protected, and the vehicle also get protected. PP proximity pilot is a pre-insertion signaling. So this is a safety control signal which is sent to the vehicle control system, which avoids the movement of EV. When the electric vehicle comes and it is connected to the charging panel, due to any reason, the vehicle should not move. In that case, it would dislocate the charging panel from its location, right? So it's a sort of safety control signal which would ensure that while the electric vehicle is connected to a charging panel, it would not allow electric vehicle to move, and it's just locked. And there is something called as control pilot. You can see this is another communication port, which will help to communicate between the vehicle as well as the charging panel. Charging panel has certain capacity, certain amount of rate of charge of current that it can allow it to pass through, and the vehicle has its own requirements. So they both would talk to each other via this control pilot to ensure that the expectation of EV is met, not at the cost of burdening the electric vehicle charging panel. So, and the charging time, as you can see here, if 18 kilowatt hour battery capacity has been placed in the vehicle, and if the charging panel is 3 kilowatt capacity, then it would take 6 hours. And if you go for a higher capacity charging panel, it would just take 22 minutes. So just an indication to help you understand how somebody has unmuted, I guess. Please mute yourself. Please mute yourself. Thanks. Whatever may be the capacity of vehicle, if you go and connect to a bigger charging panel, then the charging time would decrease. But provided that the charging panel should be able to cater to the need of, should be in a position to cater to the need of the electric vehicle, as well as battery and the charging cable and the converters are designed enough with a good capacity that it could handle the high charging current. So factors affecting charging, I have just listed out some of the points here. Battery size, if battery size is higher, then longer it would take to charge. SOC, if SOC is 50%, then it takes less time compared to if a battery is completely drained out. And maximum charging rate of vehicle, if the vehicle charge rate is 7 kilowatt, then it is not possible to charge using 22 kilowatt charge point. Now there is a limitation of the charge rate of the vehicle and maximum charging rate of charge point. So if charging point is capable of charging at lower capacity than the maximum charging rate, yet it will not be able to meet out the expectation. And the environmental factors like cold temperature or extreme weathers may affect the battery life and charging time as well. And hour of the day during the peak hours, many electric vehicles are concentrated at a specific location, and it would be difficult for a particular charging station to meet out the expectation of electric vehicles, especially if somebody is very much interested to get quickly charged and it's overpopulated or overcrowded at a specific location, then it would be very difficult at that specific instant of time. And more electric vehicles is another reason why it would affect the factors. It would affect the charging time and type of charge cable, battery drain out, and if battery is kept for idling mode for a long time, that would also affect the charging time of a battery as well. So type of EV charging, it's onboard charging, and that means you're connected to a charging station and getting charged. And there is solar power EV station. You can see here on a parking station there are solar PV panels being placed, and it would allow the vehicle to get charged. And it's a very right time because you're parked and you're gone to your office, and now the vehicle gets charged until it is parked there. And there is a wireless charging. This is another important method where there is no need of physical cable to get connected to your charging panel, where there is a receiver and a transmitter being placed with a good amount of distance, and the charging happens in a wireless fashion. And there is another recent advancement in the charging, that is road constructed for dynamic charging. You need not have to park your vehicle at all. What you have to do is you keep running. You can see here there is a green lane being placed. The vehicle would keep moving, and at the same time there is a wireless charger being placed on this road, and the receiver is at the vehicle. So while the vehicle is moving, it would get charged. So similar to your electric train. So this is another new advancement that we can see in the EV charging, so that you can avoid wastage of time. So EV charging system, including off-board and on-board charger, you can see some vehicles may have both the facility for on-board and off-board charging. So on-board charging means there's onboard charger being placed. That means it would directly connect to a AC power supply and gets charged. And off-board charger means there is a converter being placed outside, and there is a battery being placed inside. So this is the another thing. So now we'll move on to the requirement of power converters. Now we have given some introduction, some background about what is the electric vehicle, where do we stand, and what are the typical charging standards and charging methodologies, the factors affecting the charging, and all these aspects that we have discussed. Now let's move on to the converters aspect. So what are the requirements of power converter in electric vehicle? It's when somebody may be interested in onboard charger, DC to DC converter for charging. Of course, if you because ultimately battery is a DC based component, so it may require either AC to DC or DC to DC converters to get it charged, and inverter for drive control, and isolated charger would be there. Bidirectional charger or inverter, because if you want to go for V2G or G2V based operations, then bidirectional charger is also important. And power factor conversion correction converter. This is another important aspect, because when you place the converters, you should ensure that the current would exactly in line with the voltage waveform, so that you would avoid low power factor operation of the converter of the electric vehicle charging, such that the power quality aspect is being taken care. So the power converters for lights control, power converters for infotainment systems, HVAC or DC converter, heating, ventilation, air conditioning, because vehicles have all these things, facilities, and power windows, because windows also require some electric energy to raise or to keep it low. And sensor-based power supplies, other electronic accessories like mobile charger and other things. So there's a hell amount of requirement of power within the small electric vehicle. So all of them require different types of converters. So types of power converters, we categorize into non-isolated and isolated types. In non-isolated category, we have AC to DC converter, DC to AC converter, DC-DC converter, buck boost, and all these things. Isolated converter topology, we have isolated means there is a separation, right, between primary and secondary. So it consists of flyback converter, forward converter, full bridge converter, push-pull, resonant, and all these types. I'll discuss some of the converters. We cannot cover complete set of converters and keep discussing one after another. Otherwise, it will become like a polytronics course. So, but we'll highlight some of them and try to give you some overview about some key features about these converters. So just different topologies being displayed over here. Non-isolated types of converters, you can see a simple AC to DC rectification bridge rectifiers, diode based. There's no control over this charging or discharging aspect, because the diodes are uncontrolled. When EV needs to be charged by grid, it's the simplest converter that one can think of, and you get charged the vehicle. Charging can happen without any doubt, but it would have its impact on the power system level, because when you place diodes in between AC and DC, diodes are placed, which will help to convert from AC to DC, and this would make the circuit a non-linear circuit. It's no more a linear circuit. So what it would do is it would draw some or it would inject some harmonics into the system. It would become like a source for harmonic injection, and that would impact the voltage, the quality of the voltage. No more it would be a pure sinusoidal waveform. And if there is a sensitive load being connected at the same point of common coupling, then that load would get affected. So this is the simplest and cheapest converter, but yet it's not so technically supportive or well received converter as such. And then there is a boost converter, and it depends upon the voltage levels of a load. Load could be a battery, and there is a voltage source. Voltage source could be a PV or any DC bus, where the which is maintained by either either the DC to AC converter, or it has an independent isolated topology where PV panels are giving power to the battery. So it depends, and if the voltage level at the output side is required to be higher than the input side, then you go for boost converter and buck converter, where voltage level at the output side is lesser than the input voltage source. And there is a buck boost converter where you can have different varieties of combination of output voltage, could be higher or lower based on the duty ratio that you choose. And there is a bidirectional converter, which is a very popular topology being adopted when we speak about connecting electric vehicle to the grid. The reason being, this specific converter can help you to charge and discharge. Help you to charge and discharge based on a scenario. When there is a peak in the grid, that means grid is in hungry of power. There are many loads being connected, and it is really overburdening your distribution transformers, and you are in a desperate need to seek some support as a distribution system operator. Then at this point of time, you would make a call and invite many electric vehicles to come and participate in a demand response program, where they come and discharge whatever the charge being accumulated in the battery. On the other hand, if there is off-peak hour, where most of the buses are free from the loads, and at that point of time, you may invite the electric vehicles to get it charged. So in that way, as I already told, the consumer will become prosumer, and he would get some financial benefits, and the grid gets benefited. It's a win-win scenario from both the perspective. And bidirectional DC to AC converter, if there is a AC system and there is a DC system, then you use this any topology, H-bridge type or any such topology can be adopted for again achieving the bidirectional aspect, AC, V2G or G2V conversion, V2G operation, sorry. And then there is a isolated converters. Dual active bridge type is a very popular topology being seen in the system. So you can see there is a DC at the input side, then you convert DC to AC, high frequency AC, and you are going to use a high frequency transformers, which is made up of ferrite core, and then you transmit this power over a long distance, and then at the receiving end, when the electric vehicle is placed, then this can be used for AC to convert from AC to DC, and then the battery being charged or discharged. Both V2G and G2V operation is possible. The biggest advantage with this isolated converters topologies is both the circuits, the primary and the source and the load, are separated physically, right? So physically they are not connected. So the fault may be happening at the source side, will not get reflected at the battery or the electric vehicle side, and the vice versa as well. This is the biggest advantage that one can see, having isolated converters in place. And there is a forward converter and there is a flyback converter, where the switch will open or close based on this. You would get the output voltage. And if there is a transformer which has a different turns ratio, then you can have a different range of output voltage altogether. These are some familiar topologies. A push-pull topology converter I have not displayed, but there is another important topology being adopted by the industries to realize this V2G and G2V operations. And types of power converters for EV charging and auxiliary power. So for AC to DC rectifier for EV charging, I have different types like Swiss rectifier, Vienna rectifier, 3-phase 6-switch, boost converter, multi-level AC to DC converter, AC to DC multi-level converters in EV chargers. This is another topology which consists of cascaded H-bridge multi-level AC to DC converter, NPC multi-level AC to DC converter, flying capacitor based multi-level converters, and isolated converters topology, which we have already discussed, resonant converter, CLLC, dual active bridge, and all these things. And non-isolated types, we have 3-phase interleaved parallel 3-level converters with separate inductors. So I'll discuss few of them now. So the first one is 3-phase buck type rectifier. So this is a topology for three-phase buck-type rectifier. So the key requirements from the grid operator from the EV charging station are any topology that you may adopt, but a general requirement or expectation from a grid operator is achieving power factor correction. As you already told, it should the power factor should be as close as possible to unity. Unity is the best one, and low THD, high efficiency, and high power density as well. So three-phase buck-type rectifier is a proper choice for the AC to DC power stage, since it can deliver these features. And moreover, TPBR, that the three-phase buck-type rectifier, provides inherent inrush current-free startup, wider output voltage control range, phase leg shoot-through protection, and overcurrent protection circuit during short circuit in comparison with boost type three-phase rectifier. Of course, I'll be also discussing about boost type three-phase rectifier. So this has an advantage over the boost type in terms of protection aspects. And besides, input current can be controlled without closed loop configuration as well. And is there any demerit? Yes. While operating in high frequency, it is caused by distributed parasitic capacitance between the DC link output and the ground, leading to input current distortion, especially at light load conditions. So at light load conditions, the effect of parasitic capacitance is very prominent, and that would have impact on its operation. And moving forward, let's discuss about few aspects about the Swiss rectifier. So Swiss rectifier is another type of three-phase bridge type rectifier with 8 switches. You can see there are 8 switches being placed, 6 here and 2 here, totally 8 switches and 6 diodes. The key features are 6 plus 2, 8 diodes here. And then the key features are it has higher efficiency, lower common mode noise, lower conduction and switching losses of the switches compared to 6-switch three-phase bridge rectifier. Control methods of DC to DC converter can be implemented on the Swiss rectifier due to its circuit structure. And SVPWM, space vector-based PWM techniques, can be avoided for Swiss rectifier, and hence control becomes simple. And interleaving of this rectifiers, it means multiple connection of this Swiss rectifiers offers smaller current and voltage ripple, lower filter requirement, high power, high bandwidth, and high reliability. This is what the expectation from the grid operator as well. And so Swiss rectifier with interleaved DC to DC output stage that can achieve 99.3 efficiency with a rated power of 8 kilowatt, which is reported in the literature. So it's a very fascinating figure. And high power operation can also be ensured using multi-level three-phase Swiss rectifier, but the circuit becomes too complex to control. One key demerit of Swiss rectifier is that it allows only unidirectional power flow. However, bidirectional Swiss rectifier can be developed with the compromise of extra electrical components and intricate structure so that V2G operation can be possible. There are certain limitations, but that can also be overcome actually. Another rectifier is a VNR rectifier. So three-phase VNR rectifier exhibits similarity in operation if compared with a three-phase boost PFC rectifier. However, the power flow is unidirectional here. Though it remains the benefits of three-level converters, common drawbacks of three-level converters including requirement of DC link capacitors. You can see there's a requirement of DC link capacitor. This is also in a common limitation of this VNR rectifier. And VNR rectifier is widely used in high power applications because of its simple control method. Key advantages are high power density, high power efficiency, reduced number of switches, unity power factor, very low total harmonic distortion, neutral connection free structure, voltage stress on the switches is half of the DC link voltage, and no dead zone switching drive is required. These are the key advantages of this converter. So VNR rectifier, this is a unidirectional, this is a bidirectional type. So a smaller volume of the VNR rectifier can be accomplished as its requirement of the boost inductance is nearly half compared to the two-level rectifiers. Now this is a unidirectional one, and this is a bidirectional VNR rectifier. So the three-phase VNR rectifier comprises three boost inductors at the input. 3 boost inductors are being placed at the input and 6 fast rectifier diodes, as you can see here, and 6 switches two switches per leg and two split capacitors at the output. This is a typical topology. In addition, VNR rectifier is compatible with bipolar DC bus structure that allows better power flow capability while maintaining the step down ratio of the DC to DC power stage flow. And then three-phase boost type rectifier. So three-phase boost rectifier is well suited for the AC to DC power stage of the EV charger due to its simplified structure, continuous input current, bidirectional operation, high output DC voltage, low current stress, less number of switches, simple control scheme, low THD and high efficiency. So the circuit schematic of a three-phase boost type rectifier looks like this: 6 switches and a capacitor and 3 inductors. So inductors are utilized to boost the voltage and reduce the harmonic content of the input current. So the anti-parallel diodes in three-phase boost type rectifier suffers from reverse recovery loss, which worsens the switching loss of the MOSFET. This is one demerit, as you can see here in this type of converter. And there are multi-level AC to DC converters. As we speak about multi-level converters, the natural understanding for anyone is to realize that the output THD would be less. That means the power quality would be better as compared to two-level converters. So this is same for these topologies also. There are 3 topologies which are commonly seen: cascaded, H-bridge, flying capacitor, and neutral point capacitor type. So EV fast and ultra fast charging application require these kind of topologies compared to simple two-level converters. So the basic working principle of a multi-level converter lies in generating staircase waveforms. So basically you have multiple staircase waveforms. So multi-level means multiple staircase waveforms are seen, by which the THD would improve basically. So the unique characteristics of a multi-level converter includes staircase multi-level PWM waveform to attain low THD, smaller dV by dt stress on the switches. So dV by dt stress on the switches would decrease. So stubber circuit design would be easier and simpler, and minimization of magnetic components to allow superior performance. Less voltage stress on the switches in high voltage application. Example, you can see 100 volt rated switch in 400 volt input voltage. Low EMI, electromagnetic interference when you go for high switching frequencies, and reduced voltage transition between levels as well. So some topologies, cascaded H-bridge converter, you can see here. These are the different levels of cascading which is happening here. So there is an output voltage. It's a full bridge single phase inverter. There is a DC bus connected, separate DC bus or battery being connected there. So the output is connected in series. So ultimately you would get the output voltage waveform, which are cascaded outputs. So you will have different levels. 3 stages at least would be seen here, like this. So flying capacitor type allows for smaller storage requirement for the capacitor when switching frequency is increased with high. If this type scales down the filter size significantly, thereby improving the overall economic benefits as well. So a neutral point clamp type, you can see another category of multi-level converter is known as neutral point clamp. Somebody is speaking. Any doubts? Please mute yourself, and if you have any queries, we can take up. Please mute yourself. Yeah. So another category. Maybe somebody can mute them. Okay, thanks. So neutral point clamp type, another category of MLC is known as NPC type. So with the NPC type, this is very commonly seen. So the advantage is low distortion in output voltage waveform, medium voltage operation, reduces dV by dt stress across the switch, and input current with low THD. All the switches need to block half of the DC link voltage, and so switching loss is minimized. So moving forward, there is a recent advancement in semiconductor switches. People are moving from normal silicon-based type to wideband gap-based semiconductor devices like silicon carbide or gallium nitride-based switches. So, how about including them as a part of the design of EV converters? So naturally, it would bring in many advantages. So there's so many types of wide gap switches based power converters for EV application. So GaN based gallium nitride and silicon carbide based Schottky diode based boost converter. This is suitable for onboard charging. GaN HEMT and based SS class 5 to converter auxiliary power supply. Similarly, bidirectional charging also goes for based on gallium nitride based and wireless power transfer charging based and isolated charging with soft switching. You can see there are so many lists, V2G, G2V. For all these applications, there are already many converters topologies being designed based on silicon carbide or gallium nitride or combination of them, so that you would have a better efficiency, better performance over wide range of temperatures, and overall performance would be very efficient, and it's the power density is also quite high. So this is latest advancement in semiconductor technology, bringing many technological revolution as well. So wireless power converters, some more understanding about them. So inducting coupling based power converters. Inductive power transfer is an emerging technology for transferring power without any physical contact based on electromagnetic induction. This technology is employed to transfer power from one system to another across a relatively large air gap between two loosely coupled inductors, which have a weak magnetic coupling. And it is unaffected by dust or chemicals and eliminates sparking and the risk of electrical shock. It can be used in hazardous environment. So that's the biggest advantages, especially when you speak about military applications or desert applications where the dusty environment may be more prominently seen, or mining places. So one can think about these kind of converters. And capacitive coupling power converters. Electric energy is transferred through the electric field coupling between two capacitive plates or electrodes, and the transmitter and the receiver. Transmitter is a power source and receiver is a receiving device, could be a battery, are equipped with these plates which act as electrodes. And when the transmitter is supplied with an AC voltage, an electric field is generated between the transmitter's electrode and the receiver's electrode, and the power would be transferred. And then hybrid coupling power converter. A hybrid coupling power converter combines multiple coupling techniques, typically capacitive and inductive both coupling, so achieve efficient power transfer between the input and output stages. And this approach aims to leverage the benefits of both coupling methods while mitigating their limitations. So this is a topology for inducting coupling power converter, and this is a topology for power capacitive coupling power converter, and this is a hybrid one, which includes the merits of inductive based and capacitive based coupling power converters. So having a brief understanding of different types of converters, isolated and non-isolated types. Now let's see, you have EV and you have converters, and what are the impacts of electric vehicles on the power system level? So this is also very important to study. It's not that you have an electric vehicle, you have converters, and just go and plug in and get it charged whenever you want, however you want, whatever amount of charging you want, you do whatever you want to do. So that is not the business here. We should work in synchronization, in supportive to the power system. If power system is healthy, the whole system, the applications like electric vehicles or home loads, everything will be properly working. So let's discuss few impacts and how to address them. So impact on power quality, impact on voltage stability, impact on transformer life, impact of EV charging stations, impact on stability of power grid, impact on supply and demand balance of power grid, impact of current harmonics on utility grid, and impact on the overall environment. So a few impacts that I would like to discuss. Impact of EV on distribution system. So the power quality of the distribution system would get affected because you're bringing in converters. Converters means they're switching. If they're switching, there will be harmonics. If there are harmonics, and that would affect the system voltage, right? So some typical power quality issues like transients, harmonics, reactive power, network unbalance, oscillations, voltage variations, flickers, or can be seen. So what it would happen if, let's say, I'll just give you a narrative. If there are multiple EVs being collectively taken at a specific bus and they are charging power from this from a bus actually. So what is happening? Naturally, the voltage would drop, and there is an on-load or tap changing transformer being connected to this bus. So the tap changing transformer responsibility is to maintain the voltage at the specific bus at 1 per unit. So, but most of the on-load tap changing transformers are mechanically driven, so manually operated, and it would sometimes it so happens that there could be a frequent switching of this tap changing of these on-load tap changing transformers in order to maintain this voltage at a specific node close to 1 per unit, which would affect the life of this on-load tap changing transformers. It has a limited life, but because you are bringing in electric vehicles on frequent basis and simultaneously charging, and that would affect the life of these transformers. So that we need to look into it and ensure that on-load tap changing transformers would not get overburdened while we bring in multiple electric vehicles in various distribution systems. So the increased load due to simultaneous EV charging would cause additional voltage drops, which I've already told. And by proper charging algorithm and knowing unbalance in a particular phase, the EV can also be used to mitigate this issue. See, the same electric vehicle which is creating a problem, if we properly utilize this electric vehicle rather than disturbing the whole distribution system, it may improve the performance of the distribution system as well. What we need to do is design a smart, maybe machine learning driven algorithm based charging pattern for the electric vehicles, such that electric vehicles would not come not all the electric vehicles would be called at a specific time, but they're distributed over a horizon of time across geographical locations, such that the distribution system, transformers and cables would not get overloaded. Rather, these electric vehicles can be called to reduce the burden of a distribution system, as already discussed. During peak hour, it can be called to discharge, and during off-peak hour, it could be called to charge, so that we can maintain flat load profile and reduce the burden on the distribution system. So as we discussed, impact on transformers we have discussed, and there is also capacitors, like we have switching capacitors being placed. These are all fact devices which are placed in a power system to meet out the requirement of reactive power. So harmonics introduced by nonlinear load may interact with nearby capacitors if the harmonic frequency is in resonance with the LC time constant. So there are capacitors being seen, and you're bringing in the converters, and there could be, when you switch the converters, there could be resonance that may be happening because there are inductors which are connected to the converters, and the switching happening, and at a specific switching frequency, both the capacitors which are already lying down in the power system and the inductors connected to these converters may sing a song, and that would affect the performance of the system. So resonance is a very dangerous aspect. And the power cables. The primary effect of harmonics on power cables is the additional heating due to an increase in I-square
losses. So I-square losses would increase. The protection equipments like relays, switch gears, and metering equipment may malfunction. Malfunctioning means two things. When it is intended to function, it may not function. When it is intended not to function, it may function. Both the way, it is a troublesome thing. So because you're bringing in converters and harmonics being placed and all these things are happening, so it may affect the performance of the protection devices as well. And then phantom loading, because charging stations are being placed and dumped. So it may observe some bare minimum charging may keep on happening on a frequent basis, though the electric vehicles may not be present. So because capacitors are there, so capacitor charging and discharging may be happening, and because of which there is consumption of electricity. It's a dead electricity which is not going for any proper utilization. So this is what we call it as phantom loading. And then load imbalance may also happen because different phases you are connecting. If it is not properly maintained, the imbalance in load imbalance on different phases can happen. And DC offset also due to harmonics. So these are different power quality issues being observed. And some case studies regarding distribution grid impacts of electric vehicles. There is a case study being carried out in California state of US to see how, if electric vehicles are being called, how it would affect the many electric vehicles being called at a time, how it would affect the distribution system performance. You can see here time of day, late evening hours, multiple EVs are called for, and they're charging. So you can see because of which there are many red hotspots. That means these are the areas where feeders are getting overloaded. And similarly, another case study being seen in Maldives, where a significant peak demand is being shot up because of the presence of electric vehicle, and you can see there is an impact on the overall distribution system. So with this, I'll move on to some real-time simulation case studies and MATLAB case studies that we have done at IIT Kanpur. This is the last phase of our presentation today. So some research angle that I would like to show you actually regarding electric vehicles. So first of all, what is a real-time simulation? Often we do not understand what is the importance of real-time simulation. So what is real-time simulation? Actually, in real physical world, let's take an example. If there is a overhead tank and it takes some 15 minutes to get it filled, then if you want to study this performance of a tank and what is the flow of water and how much time it would exactly take to fill, and if there is a leakage in water in this tank and all these things, I'm just taking a physical example. So what you have to do is you have to take a real-time model have to be implemented so that let's say the physical tank takes 15 minutes to get it filled. So your model being implemented in a real-time software should also take exactly 15 minutes to get it filled. And then you can carry out some transient studies, steady state studies, and realize how the physical system would work. So this is what we do, because the entire power system is there. And let's say you place charging station at this bus, and how it would impact, that we do not know. We cannot take risk placing a charging station and carrying out the exercise and then understanding that we have made this mistake and then undo the things. It's very costly, expensive learning in that regard. So what we have to do is model it and study it on a real-time platform. So there are many such real-time simulation tools which work in microsecond level, nanosecond level, so that you can mimic the exact working model of a physical system. So there are varieties of real-time simulation tools. RTDS, very popular and well-known for power system-based studies. And then there is Typhoon Hill, which is good for microgrid-based studies. And there is OPAL-RT, which is good for power electronics-based studies. These real-time simulation tools can facilitate hardware in the loop experimentations, power hardware in the loop experimentations, control hardware in the loop experimentations, along with your sole simulation studies. So one such simulation study, that a simple study that I would like to show to you. So this is about AC microgrid implementation in RTDS, where we have renewables like solar panel is there, and there's electric vehicle charging station being connected to a power system, and there are loads as well. So this is the network being modeled, and these are some of the results. You can see here, you can carry out a different exercise like active power consumption and ancillary services can also be injected, and see how the voltage profile of a system, a distribution system, can be impacted because of the presence of the electric vehicle. So that was a small study that I just wanted to show some real-time displays. And then moving forward, there are two more research works that I would like to show to you today. And the first one is the challenges to electric vehicles as a source of grid resilience. Now, actually, the whole world is now looking at this specific research topic, which is grid resiliency, improvement in grid resiliency. The reason being, if you bring in many renewable energy systems like PV, wind, and people are speaking about 100% renewable penetration, 100% electric vehicle, we should really contemplate upon the impact of these intermittent, highly dynamic, volatile renewable energy sources coming together, pitching in, and injecting active power into the system and impacting the operation of the conventional grid. So the conventional grid, which are at present fossil fuel based driven, more than 50% of electricity that we receive today is based on the thermal power plants, especially coal driven. So where you have control over the electricity that you produce. So because of which, what is happening is you can manage your frequency and voltage as per you wish, right? So, but when renewables are placed, then that would really impact the system. So you need to bring in storage units to ensure that the stability of the system would not get disturbed. At the same time, let's say there could be a huge cyclone or a hurricane or some big natural disasters, some tsunamis, and all these things are coming, and maybe the wind turbines are uprooted. We don't know what's going to happen, and we are thoroughly dependent upon the renewable energy sources. This is a natural disaster event. And during such scenarios, whether your power system is really capable to meet out the requirement of some emergency loads, somebody is sleeping in ICU, or somebody is looking after the defense applications, somebody is some emergency power requirement is there. So during such scenarios, and if you are not able to provide electricity to such critical loads, emergency loads, then you cannot bear the loss that is going to happen. So in that regard, nowadays, what is happening is the electric vehicle manufacturers, they are bringing in the electric vehicles not just as a source of your transportation, rather they're manufacturing the electric vehicles to support the power requirement of your home when there is a natural disaster, when there is utmost need of electricity, where you have been completely isolated from the main grid. Now you have an electric vehicle, you have a battery within it, and it is being charged. Now utilize it to meet out the requirement of your the home loads. For example, the latest generation Nissan Leaf E Plus electric vehicle with a fully charged 72 kilowatt-hour battery can provide enough electricity to power the average European household for 6 days. As a disaster recovery vehicle, the RE Leaf can power multiple devices simultaneously. Here are some examples based on 230-volt power use, electric jackhammer, 24 hours of capacity, 36 kilowatt-hour, pressure ventilation fan, 10-liter soup kettle, intensive care medical ventilator, ICU can be supported for one complete day, and 100-watt LED floodlight can be supportive for one complete day. So this is what we call it as improvement in grid resiliency by using electric vehicle. It's a very important aspect. Based on this theme, recently at IIT Kanpur, my students have carried out this research work. It's the development of a unique energy management scheme for harnessing electric vehicle potential to improve grid resiliency. This work has been accepted in a very renowned IEEE PS General Meeting conference, and we are going to present in US next month. So the key objective of this work is to provide power backup during extreme power blackouts such as floods and hurricanes. And this work proposed a control strategy to work during fault or blackout without upgrading the infrastructure. That means you have as renewable energy sources, solar, wind. The system you can see here, you have this solar. This is solar. You have wind, and then you have home means there will be UPS, and there is a EV, right? and they are connected through different converters to a DC bus. And this DC bus is connected to an inverter. And this inverter is connected to a grid. And the AC bus also has some residential loads. So with this EV, we can carry out G2B and V2G operations. And there is some residential DC loads also. Now the objective is, if there is some natural disasters has been displaced here, can we use this electric vehicle to feed the requirement of home loads, some emergency home loads? So how do we achieve it? You need to ensure that with proper energy management studies, during normal operation, when there is no disaster, when system is very healthy and system is working fine, there is no fault, there is no natural disaster, and during such scenarios, can you maintain the battery SOC, the battery of the electric vehicle, SOC of the battery of the electric vehicle, very optimum manner if you utilize it, then that can be utilized in a better way during the emergency situations. So this is a proposed control strategy during the grid feeding mode. The grid side converter, the three-phase inverter would be exchanging power with the grid, and UPS converter and the EV converter would be in the charging mode. And during mode 2 and 3, that means the grid connected mode, it's behaving like an isolated manner as well. Then what happens is the grid side converter may be maintaining the voltage as well as, and this UPS converters or this EV converter may be maintaining the voltage during isolated operation. Especially this is isolated operation. It's isolated operation. So what would happen is the first priority is given to UPS and the second priority is given to EV. That means if there is a load which needs supply, so better utilize the UPS than the electric vehicle, because electric vehicle can move here and there and meet out the expectation at a specific location. So mode 2 is a faulty condition, mode 3 is a natural disaster condition that we have considered. So there are certain SOC limits that we have designed such that at least 50% of the EV battery SOC is retained for the requirement of emergency scenarios. So these are some real-time simulation results. You can see here that battery, this work is being implemented in OPAL-RT hardware, real-time simulation results. You can see that this is a grid voltage and grid current. It's almost sinusoidal, and then the UPS is maintaining here. You can see the UPS is maintaining when the PV insolation is changing, and then if there's a fault which is happening, this is a fault condition. You can also see that the EV at this point of time is being protected, and then there is a change in irradiation conditions. Again, the UPS is pitching in and trying to maintain the voltage at the DC bus level at a nominal value. So these are some additional results. As you can see here, the battery SOC is being maintained at a proper level such that it would be helpful for the emergency scenarios. Some final conclusions regarding this work: UPS battery capacity and 30 kilowatt-hour EV battery capacity is being considered. This energy can be used for critical loads inclusive of 2 15-watt bulbs, 1 18-watt mobile battery charger, and 1 kilowatt kitchen appliance during extreme emergency for approximately 6 days. So with the novel control scheme that we have implemented, that we could realize that a specific home load can be maintained for 6 days with bare minimum appliances. You need at least 1 light 15-watt LED bulb, and there is a mobile charger. People may live without food, but they cannot live without mobile, right? So we have considered this as emergency load. Mobile is a very emergency load. And then 1 kilowatt kitchen appliance for some cooking purpose is being considered, and we can manage this. And another work, it's about modified isolated bridgeless SEPIC power factor converter for EV battery application. We have designed a novel converter. It's a SEPIC power factor correction converter, specifically for EV battery application. This is the topology so that we have proposed. It's a closed loop control. The objective is to enhance the performance of a conventional bridgeless power converter, where we can reduce the THD. Overall improvement in the efficiency can also be achieved. So I'll not go in detail. We have implemented using software tool, PSIM tool, and we have also designed a hardware where we have tested up to 750 watts in a real hardware setup, the working of this topology. And then the THD is significantly reduced as compared to the conventional approach. Now the THD is around 2%. This is what our result says. And we have also tested with a closed loop control strategy, maybe with 300 watts, I guess. And these are some of the results. The applications: bridgeless power factor conversion circuits or correction converter circuits are widely used in AC to DC power supplies, such as those found in computer systems, telecommunication equipment, industrial machinery, and consumer electronics, and they help improve power quality, reduce harmonic distortion, and enhance overall efficiency. So this can also be attached with PV or wind, and further analysis can be carried out. So with this, I'll conclude my talk today. And these are some of the research projects that we are currently engaged with related to electric vehicle and storage, and some international research projects as well. Our collaboration currently is with MIT, West Virginia University, Washington State University, and we are also working in closely with Indian Railways, Railway Energy Management Corporation Limited, where they asked us to develop a machine learning based control strategy for forecasting the solar and wind, and as well as load, so that it would help them reduce the penalty that they're currently incurring from the power system. So our research works currently have 5 PhD students and some MTech students. They are working in the area of renewable integration challenges, electric vehicles, and machine learning applications as well. Some publications and reference. Thank you. Thank you so much for your patient hearing. And if you have any queries, probably we can take some questions. Thank you so much. Yeah.
Thank you, sir. I request participants to post their queries. Is anyone willing to ask?
I hope they were listening and not sleeping.
Yes, sir. Yes, sir.
Because most of their videos is turned off, and I don't know. This is one problem with the online event.
Online session.
They'll be doing so many parallel things. Okay, somebody is asking a question in chat box. I can see that. Madam, the real-time EV battery SOC checking software is there or not? She's asking. So real-time, you need to design the algorithm. Of course, you can design some apps where in real time you can connect to your battery and then see how you can the battery SOC is changing. And most of the EV manufacturers, they're providing these apps as well. So I think that is possible.
Hello, sir.
Yes, yes.
Sir, myself, Shashidhar. Same, I have asked a question. Same question. That is real-time application. If any vehicle is there, I want to check at the same time that battery is good condition or not. How we can proceed with that option or any method?
No, basically you need to connect to the BMS of the battery. And
Okay,
because battery BMS has this storage SOC information that you need to connect to your mobile app. You can design an app and you can get the real-time information. That's not a big deal.
Okay.
Battery BMS will have real-time information about what is the state of charge.
Oh.
Yeah.
Okay, sir. Thank you.
Thanks. Any other question?
Sir, I just have a query
Please, yeah.
regarding design of power converter for EV. Should we should compulsory go for a bidirectional DC-DC converter, right, sir?
But it's not compulsory, but it would be helpful for you to use, I mean, if you use bidirectional converter, you can carry out B2G and G2V operations. Vehicle to grid, grid to vehicle, charging, discharging can happen. So
Okay.
it's recommended, but it's not compulsory.
Okay. Then if we go for a unidirectional converter, how about the control strategy, sir?
So the control strategy would be like closed loop control, where you sense the current and see that bidirectional or unidirectional, the control strategy will be closed loop only. So you would sense the conductor, the current which is sensed at the inductor, which is connected to the converter.
Input
And
current.
then there will be specific charging current, the reference current, and the closed loop control would ensure that the reference current is being tracked.
Whether this converter, it depends upon this different types of gain techniques also, sir. Means because we need up to 380 volt, right, or up to 400 volt. Whether these gain applications, what we are considering voltage multiplier cells or coupled inductor cells, these topologies, will this matter a lot or they don't?
Yeah. I know if you go for playback converters and push-pull converters, the gain would be there. Voltage, I mean, you can connect to different voltage levels. And of course, depending upon application, and one can choose a specific topology, isolated or non-isolated.
So non-isolated, where we can go for application wise, sir, non-isolated.
Yeah, application wise, let's say you have your home vehicle and you are and where you can see that you're not much bothered about the protection aspect. The fault which is pertaining to the grid should not reflect on the grid. And if you're not worried about that thing, then you can go for isolated, non-isolated converter topology.
Okay, sir.
And it's cheaper as well comparatively. Yeah.
Compared to isolated type.
I think there are some questions in the chat box.
Yes, sir. What way flyback converter will be helpful in EV?
Yeah, flyback converter will be helpful in EV. As I told, it will be for different voltage gains, and basically, if you are interested for different this thing, what do you say? Tappings can be done, and another advantage that one can see is, as I already told, the protection aspect, because you're using the transformer there, right? It's primary and secondary separated, so the protection is also being taken care. So all isolated converters come with this common advantages. Anything else?
Participants, any more queries? I think there are no more, sir.
Yes.
I would like to just wind up the session, sir.
Sure, yeah.
So thank you very much, sir, Dr. Gururaj, sir. After my mail, you immediately replied with a positive response. We are very much thankful and grateful to you. So in this today's topic, you have covered many, each and every point is research oriented. Right from starting this, you have started with the level and types of chargings. And one more thing, it is road constructed for dynamic charging. It is very interesting, but will it be possible in India, sir?
Yeah, why not? It is possible.
Upcoming days.
Please write a letter to Mr. Modi.
And types of power converters, both isolated and non-isolated type, and different types of rectifiers such as Swiss and Vienna rectifier, 3-phase boost rectifier, and MLC for EV charging mainly. And also the topics regarding EV impact on power system, that is which is a resonance and phantom loading. And this real-time simulation, I think, as you told, it is very much helpful, sir. This Opel RT or else RTPS and Typhoon. Nowadays, everyone has to learn this software so that, as you told, the real-time simulation will be much more helpful to go for a hardware setup before going to the hardware setup. And grid resilience, and the example which you gave about Nissan Leaf EV, which is which is designed to meet the home requirements. So all these together will help us in moving towards EV, because nowadays the people are shifting towards EV, but as you told, during disasters and also the battery bank, how far it is sustainable for a long drive. So they are hesitating at that instant.
Correct.
So this will give a clear picture about those things. And thank you very much, sir, for the session. And we look forward for future sessions also. I think
Thank
you'll
you.
support in future also.
Why not? Why not? Happy to be part of any future session.
Sir, in this regard, I would like to thank our college chairman, sir, and Satyanarayan Raju, sir, and also Secretary, sir, Dr. N. Prasad Raju, sir, and Treasurer, Sri N. Kanakaraju, sir, and Director, sir, Dr. J. Raja Murugadas, sir, who gave us this opportunity and support to conduct event on behalf of our EEE department, sir. Thank you very much, sir.
Thank you. Thank you so much. Thank you very much, and for giving me an opportunity to speak over for some time. And if you have any queries and if you want to interact with me to carry out some research activities, you're open to discuss with me. Write an email to me if you're interested in this area of EV integration challenges. So thank you one and all again for your kind patience, and I may say goodbye now for time being.
Yes,
Thank you.
Thank you, sir.
Bye.